Will you start the recording? Okay, welcome everyone to this week's Dublin Area Theoretical Physics Colloquium. We are very happy to have Henriette Elvang today from Michigan, who will talk about Bootstrap and double copies. Please go ahead.
So thank you so much for the invitation, and thank you for the accommodation of times and everything so that we can make it work across the international time differences and everything. So I will talk about work that I've done in collaboration with people here at Michigan, Juan Hang Chi, who's a postdoc, Aidan Herriske, Callum Jones, and Shruti Branchapi, who were and are my students, and then some forthcoming work with a second-year student, Alan Chen. So this is a story that connects physics at very different scales. On the one hand, it'll connect physics at the particle physics level, where we approach the smallest scales. And on the other hand, it will connect gravitational physics, such as, for example, gravitational waves, binary in spiral, that happen at big astrophysical scales. And then in addition, I hope to show you that they're in this process of connecting those two stories of physics as some very interesting mathematical structures. And so I also really like to have questions along the way. I don't have to say everything on the slides, but so if you have questions along the way, please just unmute it and ask. So let's see, if we zoom in on these particle physics processes, such as these jet processes. And what we're focusing on here is the high energy process that involves the partons. For example, the gluons inside protons scattering with protons. So that would be a gluon scattering a gluon. It could produce other gluons or quarks, and out of that we get jets. So in particular, gluon scattering is interesting. Here illustrated just very schematically, two gluons coming in, two gluons going out. What you get out is an amplitude as a function of the scattering angles, which is experimentally probed via the differential cross-section, which is this phase space integral over the amplitude squared. So the focus of what we'll talk about are the scattering amplitudes in the story. So I mentioned gluon scattering, that is encoded in Yang-Mills theory. And here is an outline of what you really do to take and compute these amplitudes, which I know many people are very familiar with. But basically you have Yang-Mills theory, and then you expand it out in the expression. You have a two-field term, which gives you a propagator. We have a cubic vertex, as well as a quadratic vertex that tells us how the gluon interact with each other. And then the Feynman rules tell you to add up all the diagrams with the particular external lines organized in the loop expansion. And in this talk, we'll be focused really entirely at tree level. So let's just say we add up all the tree diagrams. And then converting these diagrams to mathematical expressions will give us something which is like a compact one-line expression. So that was the Yang-Mills side and the particle physics side. What about the gravity side? So just like in E&M, we have a force that is mediated by the photon, and QCD has gluons. These are massless spin 1 particles. Gravity in a quantized context has gravitons, which are massless spin 2 particles. So what exactly do I mean by gravity here? So what we could start by having in mind is Einstein's general relativity. And the equations of motion, which is Einstein's equation, comes from the variational principle of the Einstein-Hilbert action, which is minus square root of the determinant of the metric times the Ricci curvature. Here, the coupling is determined as Newton's constant, which in units where C and H bar are 1 is basically the same as the Planck scale. So G is 1 over the square root of the Planck scale, and that amounts to 10 to the minus 19 GeV. So that's what the Planck scale is, and that sets the scale of Newton's constant. So if we expand out this Einstein-Hilbert action, then we get quadratic terms. So we're expanding around flat space because we want to calculate small fluctuations in the gravitational field. So we're expanding around flat space, and these fluctuations then give us quadratic terms. And those equations of motion you would get to there are, of course, the things that describe gravitational waves. Of course, you have to do some gauge fixing and so on, but this is well known. And those have, of course, wonderfully been observed in the very recent times. If you continue to expand up to higher order, you can treat this action perturbatively and calculate graviton scattering. The quadratic term, just like for Yang-Mills theory, gives a propagator. And then in gravity, we have cubic and quartic interactions. But also, since this expansion is infinite, there are terms with any number of gravitons in it. So there are endpoint interaction and any n. the Feynman rules for these type of vertices are extremely complicated. And here, going back to Shannon, he computed these 4 diagrams that contribute to the 4 graviton amplitude explicitly and wrote down what they are in a standard Dedunder gauge. And the message from this is that each diagram here is a match about 3 times as big as what I've seen here. And then you have to add it up to give the amplitude. So you can imagine how complicated that is. Why do we even care about graviton scattering? So I gave you the scale of a gravitational coupling. And when I listed here, I've also listed the strength of each of the vertices. So cubic vertex is worth 1 power of kappa, which goes as the square root of g. That means kappa is of order 10 to the 19 GeV inverses. And even if I was at LHC energy, which is of order 10 to the 4 GeV, the effective coupling, which is the dimensionless quantity of the typical energy in the process times kappa, will be exceedingly small, of order 10 to the minus 15. So you might wonder, why do we even care about perturbative gravity and gravitational self-interactions? And the reason is that when we stick, even if we just stick to the classical level, which is what is captured by tree-level physics, then that is the same physics as Einstein's equations. And so we know that matters for our daily life. So even if gravity is extremely weak, then it matters. So let's try to see how it matters from the point of view of perturbative gravity. Suppose we have 2 masses, M1 and M2. You could think of those as just some scalar particles with those masses, modeling some real gravitational planetary object if you wanted. They could exchange a graviton. Each vertex is worth a factor of kappa. So that means the result of this is order g, Newton's constant. And if you take a non-relativistic limit and Fourier transform this expression, you get at the leading order and small speeds of these particles, then you get the leading order just Newton's potential for gravity. And even if g is something that at the scale is very small, for macroscopic masses, this is of course extremely relevant for our daily physics. So a Feynman diagram like this just encodes our regular Newton potential. Now there are 2 classes of corrections to this in classical physics. The masses can be moving, which means that there is really at play here a non-relativistic expansion in small b over c. Those are called post-Newtonian corrections. But then there are also corrections in higher powers of g's, which come from further exchanges of gravitons that generate more powers of kappa, which means higher power in g, and those are called Postman-Kapskian. Now, these are not independent of each other, because, for example, if we think of those in context where you think about binary black hole binary in spirals, you would have v squared of the same order of g by the virial theorem. So in certain contexts such as that, these 2 types of expansions are not independent of each other. And so look at those higher powers in g's. I said you could exchange more gravitons. That gives you higher powers in g. These are the g squared that have been known since 2002. 3 exchanges are order g cubed. There are many, many more diagrams than these, and those were very recently calculated systematically. And in fact, there are also results that go up to g to the 4 now at the state of the art. But when you look inside these diagrams, you see that one thing that is important to include here is also the gravitational self-interactions in the story. And those are exactly the graviton amplitudes. If I look at what sits inside here, I have my S, T, and U channel diagrams as well as the contact terms. And that is exactly a 4-point amplitude if I were to add up what is inside here. And that 4-point amplitude is therefore important. And so this is something that we care about because these 2 type of diagrams do encode very relevant classical physics for us. But on the other hand, we've seen that this is really complicated on the gravitational side. And so now let's connect the 2 subjects we talked about so far, the gluon scattering in Yang-Mills theory and the gravitational scattering. It turns out that there is a remarkable relation between these called the double copy. And that is basically a map that takes sums of products of amplitudes for gluons and map them to those of gravitons. And here, sometimes this is phrased as Yang-Mills theory squared is gravity. And again, there are proposals to bring this to the loop level too, but for now, in this talk, we'll focus entirely at the tree level. Okay, so what does this map look like? So here I've written out what it looks like in general for endpoint scattering at level in one form. And what you can think of this as a multiplicative map where I have amplitudes from on my left sector field theory, from the right sector field theory. You can think of both of those as Yang-Mills, mapping to some amplitudes in gravity. Now, these amplitudes that sit here on the left and the right, the Yang-Mills amplitude, are color ordered amplitudes. That means that I can take the trace of the gauge group generators, these generators T. There's a single trace because it's tree level. I can factor it out, and by cyclicity of the trace, I only want to sum over n-1 factorial such permutations of the legs. And then the coefficients of each one of those traces are gauge invariant objects that are known as color ordered amplitudes or partial amplitudes. And for a given color order A, which is what is summed over here in the KLT product, there will be one of the amplitudes from these coefficients sitting there. And so, of course, naturally, I have n-1 factorial such color orderings, but we see that we're supposed in the KLT formula only to select n-3 factorial of those for label A and n-3 factorial for label B and sum over them. And what this looks like is something like a vector from the left, vector on the right, and they're multiplied together with some matrix, which is also n-3 factorial by n-3 factorial, which we denote the KLT kernel. It's something that I will show you more details of what it looks like, but it's basically some function of Mandelstam variables for the process. And this is the KLT formula named after Cavai-Levellin and Tai, who first discovered this type of relation in terms of closed strings being equal to open string tree amplitude squared in a certain sense with a similar type of kernel. And what I'll discuss first here is the field theory kernel, where I take the field theory limit of this KLT formula, and I'll at various points refer back to what the string story actually looks like. Okay, so that's what this double copy looks like. Let's unpack it for 4 points just to see what it looks like. So 4 point means 4 minus 3 factorial is 1. So there's just one term in the sum. And let me pick my A label to be just the color ordering 1, 2, 3, 4. And I'll pick my B labeling to be the color ordering 1, 2, 4, 3. Okay, so that is exactly what this relation looks like. It says that a product of two Yang-Mills amplitudes with slightly different color orderings times something that depends on Mandelstam variables, which in this case is S, which is the center of mass energy squared for the process, that is equal to the graviton amplitude. And in fact, this has to hold for all types of polarizations of the gluons that I put in on the left and the right side here. In particular, if I think about it in terms of 4D, I can label the states in terms of helicities. And so I have a map that tells me that gluons plus times gluon plus will give me something with helicity 2. That's a graviton with positive helicity. And likewise for the negative helicities. But if I match them and took gluons on one side with a positive helicity with negative helicity gluons on the other side, I get a scalar. And those two scalars encode the dilaton and the and what is the scalar dual of the antisymmetric 2 form, which is the d-dimensional story. So that's an axion. So it's a dilaton axion type of complex scalar that sits here. Okay, now I gave you this Feynman diagram expression for what the amplitude looks like. And it is rather amazing that when you add up all those 4 diagrams, you would get something that can alternatively be written in the form of the product of 2 simple gluon amplitudes, each of which is about a line of mathematics times Mandelstam variable S. So that is a really remarkable feature. And in fact, Sannon's paper from '86 was to derive that relation that has been found by Cavai-Levellin and Tai purely from the field theory perspective and tested. That was the entire purpose of the paper. And poor Sannon had to work extremely hard because the tools available at the time was not, I mean, well, there were tools available, but they didn't use modern methods that we have now that would have simplified this relation incredibly. So this was a tour de force calculation for me. Okay, so it's remarkable that it works based on looking at the amplitudes, but let me try to illustrate one reason why it's also very surprising that something like this can even work. So we have these color ordered Yang-Mills amplitudes. And so if I pick the color ordering 1, 2, 3, 4, what the color ordering means is that I'm only allowed to have particles exchanged where the 2 lines are adjacent to each other. No lines can cross. And so this amplitude can only have poles in the S channel and in the U channel. U is for me the 1/4 channel. So by cyclicity, 1 and 4 are adjacent, just like 1 and 2 are adjacent. but 1 and 3 are not adjacent, so there cannot be a T-channel exchange. Now, every time you have an exchange, you will have a simple pole. And so the 1, 2, 3, 4 ordering has simple poles in the S and the U channel, but not in T. If I exchange 3 and 4, the story is similar. I have poles in S, and I now have 1 and 3 adjacent to a pole in T, but no pole at U. On the other hand, graviton amplitudes have no color structure. And so the amplitude 1, 2, 3, 4 can have exchanges in all 3 channels, and it will have simple poles in the S, T, and U channels. So we wonder, how can a product of 2 Yang-Mills amplitudes possibly get the structure of M right? How can you avoid double poles and ensure that you get all the correct poles, let alone the factorization on those poles? And the answer to that is the double copy kernel. The role of this kernel is really to ensure that this pole structure come out right. So for example, if I take the 1, 2, 3, 1, 2, 4, 3 structures multiplied together, you'll see that these two, they will have a double pole in the S channel, and they'll have single poles in the U and T channels to get one from each. And the kernel in that case is S, as I told you before, and that S exactly cancels the double pole that would otherwise have been there in that product. Now I could also, as we saw in the double copy, I have a choice of which color orders are multiplied together. And if I picked 1, 2, 3, 4, 1, 2, 3, 4 to multiply, that's the first line here, then I see that I would double the poles in both S and U, that's bad. And I wouldn't even have a chance of having a T-channel pole, which a graviton amplitude must have. So what does the kernel in that case do? The kernel in that case has a factor of S and U, which cancel the bad double poles and leave simple poles. And then it even supplies that missing pole at T equals 0. So the kernel is exactly the thing that goes in and eliminate double poles from the product of the 2 4-point amplitudes in Yang-Mills and provides the missing pole whenever needed. So it is rather remarkable that such a thing exists, so that no matter what 2 color orders I chose to put in here, the kernel will adapt and its form in such a way systematically to always produce the graviton amplitude. There are various other bonus properties of this kernel. It ensures a certain enhancement of soft behaviors, and sometimes it enhances also some unbroken global symmetries. Now,
sorry, so is the kernel actually more or less fixed by this, or is there some freedom?
So if I took a complete bottom-up approach, this would have been my naive guess, right? This is how I would fix the problem of even getting the pole structure right. And once I have the pole structure right, I would then have to ensure that the correct factorization happens on each pole, that I actually really get the right amplitude. And that is an extra layer on top of that. So if I didn't know about the string kernel coming from the KLT formulation, it would have been sort of crazy to think this would work. And you might say, well, fine, maybe I can sort of bootstrap it to work down at 4-point. And that would be amazing if I didn't know anything else. But how would I then ensure that going to 5-point, where 5-point has to correctly factorize into 3-point and 4-point, and my kernel, what would I pick to be? And you know, where does this structure even come from? So it's really remarkable that this works. But you raised exactly the point that we're after here, is how unique is this? It's clear that if I start trying to mess around with this kernel, I could very easily mess up the elimination of double poles or the providing the missile pole part. I could even risk messing up that I would introduce spurious poles and as I mess up this kernel. And this is exactly the type of thing that we're going to be after in this talk, is how unique is this? How much am I allowed to generalize this kernel while still preserving the structure that as long as the input come from sensible local theories, that I get an output which is a 3 amplitude in another local sensible theory. That's that theory. And factorization indeed plays a very big role for that. Other questions? Okay, so we'll keep that in mind, that the kernel is playing a very important role in the story. But I gave you here 2 different versions of the double copy, right? I just picked 2 different color orderings, and there are many different choices to pick among the n-1 factorial. But let's just focus on these ones. There's only one graviton amplitude. So these 2 representations of the graviton amplitude have to be identical. So the right-hand sides here must be the same. So here I have those 2 representations. If I take the difference, it must be 0. They have a common factor of a non-zero amplitude with ordering 1, 2, 3, 4. I can factor that out. And then I see that it must be that in Yang-Mills theory, the 1, 2, 4, 3 ordering must be proportional to the 1, 2, 3, 4 ordering with a ratio of U to T. Now that happens to be true for Yang-Mills. And this is an example of what is known now as a BCJ or Baron-Koresko-Johansson relation at 4 point. I could have picked other color orderings, and there's only one graviton amplitude, so I had to get the same result. And that then leads to a set of relations. Some are very well known. There are algebraic equations coming from the color traces, which are the KK relations that involves trace reversal and U1 decoupling. And then, of course, the BCJ relation I had. And I'll collectively call these the KK BCJ relations in the following. So let's go back to endpoint now that we sort of explored a little bit at 4 point. In general, there had to be a sum over n-3 factorial color orderings. But there are many choices you can make of those because there are n-1 factorial possible orderings you could have had. And we want to ensure that the result of the double copy is independent of which choice it is. And that is exactly what these KK-BCJ relations ensure. So now I could go back to my wide space of all possible quantum field theories and focus on the ones that have some color ordering in the same fashion that Yang-Mills theory has. And I can ask which one of those theories satisfy these KK-BCJ relations. So that gives me a selection criteria for theories that can be used as the left and the right input in this double copy relation. In other words, when I go out to the landscape of field theories, I can ask which theories can possibly be the input for the double copy, and then taking those as the input, what can possibly be produced as the double copy. And so here are some examples of things that passes the KK-BCJ criteria. We already mentioned Yang-Mills, a supersymmetrization of Yang-Mills, sticking with adjoint matter. So say, for example, pure super Yang-Mills theory satisfy the criteria. The low energy theory of pions, chiral perturbation theory satisfy this. This is a nonlinear sigma model with a particular color structure. And then there's also a model which we'll come much back to, which is called the bi-adjoint scalar model, that also satisfies, whose amplitudes also satisfy the KK-BCJ relations. We could also ask in context of effective field theory, what if I add higher derivative operators to these theories? Which operators are allowed? So this was explored very early on for Yang-Mills theory by Dixon and Bredel. And they found that the F cubed, it actually has the exact same color structure as the standard Yang-Mills theory. So this clearly passes these criteria. But F to the 4 does not. If you go, and here I'm just including the MHV type of counting, so it's only a subsector, but there are more operators in general. If I go to the next order with 2 derivatives on F to the 4, there are 2 independent operators that could contribute. One of them would pass these KK-BCJ criteria, the other one does not, and so on and so forth. For chiral perturbation theory, we talked about the 2 derivative theory passing, but then I can dress it with derivatives, and at 4 derivative order, nothing passes. At 6 derivative order, 1 operator passes, 1 does not, and so on and so forth. So we clearly see that the KK-BCJ relation criterion is something that allows certain operators, but not others. So there's a clear selection criteria. One thing that we're interested in is why are some operators allowed while not others? And also whether this is really the most general story that one could conceivably have. Is there any more general double copies? So if we think about it in the effective field theory language, what are we doing? We're taking Yang-Mills theory with higher derivative operators and sticking in on the left and the right. And then we hope to get some gravity out with high derivative operators. That's a natural guess. But when you basically do a derivative expansion or a Mandelstam expansion of the input and want to do that for the output too, it seems general that one should also generalize what the product kernel is. And so in terms of this story, we should look to what string theory does, and it does exactly that. String theory has something that in the low energy expansion is exactly in a sense higher derivative corrections to the kernel in a way that I'll make very precise a little bit later. So string theory has corrections to the kernel. So what we should do is now to ask the question, how are we allowed to generalize this kernel? Let me show you what string theory does. So string theory has a kernel that was derived by KLT. And in the channel that we looked at before, 1, 2, 3, 4, 1, 2, 4, 3, it takes the form of minus sine of pi alpha prime s. So if I expand this in small s times alpha prime, which is dimensionless, then I have a leading order term, which up to the pi and alpha prime is exactly the KLT field theory kernel I showed you before. But then clearly it has higher powers in S that are corrections to this, starting at S cubed. But it's clear that there's something that's very special about this kernel. If I had just imagined that I wanted to correct this kernel by higher powers in Mandelstam, I would have started by saying, okay, so I could have S squared. Why not also put in T squared? Of course, S plus T plus U is 0, so I don't need any separate powers of U. But why does it only start at S cubed? And also because this is sine of something that only depends on S, it certainly will only have odd powers in S in the expansion, and it has no dependence on T and U. And that might seem surprising. Why doesn't this happen? From a generic point of view, you'd imagine that you'd have to add everything allowed. Moreover, there's absolutely no freedom in the couplings here. So it's clear that whatever correction the strings gives us is very special. And in fact, it's very closely attuned to the structure of the open string amplitudes themselves. So what is the goal here? The goal, what we want to do is try to generalize the kernel from a bottom-up approach of just simply saying, what is the most general allowed structure that we can have that allows such a double copy with a given, and I focus here on theories that have adjoint matter and single trace. So what is for the input? So what is the most general structure we can have? And what are even the rules for changing the KLT kernel, keeping in mind how we've seen that it's important to eliminate double poles. We must provide any missing poles and absolutely not introduce any kind of spurious poles that would create unphysical poles in the output amplitude over here. Okay, so that's our goal. And so now for the second part of the talk, what I want to try to do is present our proposal for generalizing the double copy, and that will lead to a type of bootstrap for KLT kernels. We will then, I'll show you how we systematically solve for high derivative corrections to the kernel, explore new versions of the kernel, and ask questions such as what makes the string kernel special. So I'll pause for questions for a moment. Okay. So I gave you examples of theories, and now let's forget about high derivative corrections for the moment, but theories which at the two derivative level have a double copy. One of the things we can do is that we can ask what that double copy gives. So Yang-Mills times Yang-Mills gives gravity.
Sorry, perhaps I can ask one question. Does the same kernel work for all four of your examples? Okay.
That's exactly the key part, that I wanted to be really a product structure on the space of theories, so that it's the same kernel that I'm using in each of these cases here. And so you know, the supersymmetric structure of n equals 4 super Yang-Mills gets inherited. I get n equals 4 super gravity. It adds up. If I take n equals 4 super Yang-Mills with itself, I get n equals 8 super gravity. Chiral perturbation theory with itself gives something called the special Galileans. But if I multiplied it with Yang-Mills or super Yang-Mills, I get either Born-Enfeld or n equals 4 super direct Born-Enfeld. And so there's this whole web of theories that you can multiply together and get new theories from at the level of two-level amplitudes in these formulas. And then there's this bi-adjoint scalar model, which we're now going to talk a little bit more about. What is it? It's a scalar theory where we have a scalar that carries two adjoint indices, as opposed to gluons, say, that only carry one. This has a structure that you can think of as a global type of flavor structure with a UN, say, and a UN prime. And this guy carries adjoint indices under both of them. And then it only has just a simple cubic interaction, which depends on the antisymmetric structure constants of those two, say, UN and UN prime groups. So that's what it is. A simple cubic theory like that. Now, this theory is very special in that when I multiply it through the double copy with any other theory, I get that any other theory back, including by adjoint times by adjoint gives itself back. What that means is that this double copy map has an identity element, and that identity element on the space of field theory is the bi-adjoint scalar model. And so basically I can summarize the action of this bi-adjoint scalar model in on the product structure as an identity element, which satisfies exactly the type of relations you would want an identity element to do.
And just for clarity, you are allowing different gauge groups on different adjoint representations on the two. They don't have to be the same group.
No, they don't have to be the same group. They can have different rank. One could be UN, one could be SPN.
Okay.
The actual group doesn't matter. All that matters is that there's a non-abelian structure that I can use for the color ordering.
Okay, thank you.
Yeah, sure. String theory also has the same algebra, and it also has an identity element. And that identity element is one that we will understand later as bi-adjoint scalar with certain high derivative terms, just as I alluded to before. So what we propose is that this algebraic structure is fundamental, and it's a fundamental principle also for generalizing the double copy kernel. And what I'll try to show you is that the equation that says 1 equals 1 times 1 becomes a kind of bootstrap equation. And the other two equations that are the identifying elements of an identity element will generalize what we know as the KK-BCJ relations, which in string context are called the monodromy relations. And so basically the logic behind this is the following. If I have something that is an identity element under a given product, if I try to change the product, it's natural to change the identity element and vice versa. If I change the identity element, I must change what the product rule is that makes this thing the identity element. So what we'll see is that this equation cleanly links in a unique way the identity element to the kernel. And that's not so surprising. If I have a product and I change what the product rule is, then I must change what the identity element is. And we'll see that they're in one-to-one correspondence. And that allows me to bootstrap the possible identity elements and kernels. And then I can tell which theories are allowed as input for the left and the right of the structure. So let me try to show how this 1 equals 1 times 1 can give us something non-trivial. First, let's talk about where this bi-adjoint model come from, who we even ordered that. So there's a different formulation of the double copy, which is by Baron, Carrasco, and Johansson. And the statement is that you take a color ordered amplitude and you write it in a certain way where you sum over trivalent diagrams. There are scalar propagators, there are color factors, and there are numerator factors. And that you can write this is completely trivial. There's always a rewrite of an amplitude to give this form. But the non-trivial statement is that they conjecture the existence of numerator factors, such that whenever your color factors, which could be for 4 points, take this form, whenever they satisfy the Jacobi identity, then the corresponding numerator factors would satisfy the same relation. So this is called color kinematics duality. And then the double copy in this language takes the form that because the color factors and numerator factors satisfy the same algebraic relations, I can replace my color factors by another copy of numerator factors. And this will give me the resulting double copy of the amplitudes. And in particular, if these are numerator factors, both from Yang-Mills, the double copy will give the gravity amplitude. But because they have the same algebraic relations, color factors and numerator factors, I could also just have replaced my numerator factors with another set of color ordered factors. And if I do that, I get a scalar amplitude, the only scalar propagators, the only trivalent diagrams. So these are clearly amplitudes in a theory that only has a cubic interaction. And the way the signs and everything works out, it turns out these are exactly the amplitudes of the bi-adjoint scalar model. So historically, this is not how the bi-adjoint scalar model first occurred in the field, but this is the most natural way to understand why it plays a role. Okay, so now let's go to this idea of the bootstrap. So what does it mean that 1 equals 1 times 1 for the bi-adjoint scalar model? Because I have two flavor groups for this scalar theory, I have to color order under both of them. So I have doubly color ordered amplitudes. These are these MNs that I show here. Now, one of the color orderings will be summed over in the KLT product, just like we did before. So there are n minus 3 factorials, alphas and betas that are summed over here. But then under that double copy structure, each of the two input amplitudes have an inert color ordering here, gamma and delta, and they are then inherited by whatever this product is. Now, if you just stare at this equation, you'll see that this is nothing but matrix multiplication. So I have some submatrix of dimension n minus 3 factorial times n minus 3 factorial. and they multiply by the kernel, which is also that dimension matrix, and I get another matrix out. Schematically then, if these MNs have inverses, I could multiply by Mn inverse on the left and the right of this equation. And then you see that the kernel becomes nothing but the inverse of the Mn matrix. Of course, we need to know that these matrices are invertible, and indeed they are. If I take the adjoint scalar amplitudes at tree level, and when I compute the n-3 factorial matrices, no matter which choice I make of color orderings, these will be invertible. And this is how we can see that the kernel and the identity element of these algebraic structures are uniquely linked to each other. Whenever I know the matrices, I have my matrices of the identity element, the kernel will be fixed or vice versa. Or if I give again, I pick a general kernel, I just have to invert it and I will get the tree amplitudes of that identity element theory.
Doesn't this require the two groups to be the same, the left and right?
No, it doesn't. I mean, all that matter, I'm summing over the color orderings, and basically the structure will be that naturally I would call the alpha here a left index because that sits on the left side of the group. For the left color ordering, right, that multiplies into the left amplitudes, and the beta I would call right. Okay. But that means that the color orders of the MNs, and which is natural from the inversion, is right left. So right is a gamma is a right index, gamma is a right index, delta is a left index, delta is a left index. So their MNs are left, right, opposite what you would intuitively see because the color has the right, left, and right. Does that make sense?
Well, I'm just because M is the square matrix. If you have if you have color 5 and color 8, then you've got a 5 by 8 matrix for your M. So I don't see how it's invertible.
Oh, I see what you mean. No, so it's not so much the rank of it's not the dimension of the adjoint that matters. It's just the fact that the color orderings I'm summing over here are linked to N. So remember that the color ordering is I'm factoring out a trace of the generators. And as long as those generators don't commute with each other, I have n-1 factorial different traces.
Okay, I see.
So I'm summing over the color orderings, not any particular internal properties of the color group.
I see, yeah, okay, thanks.
But there is a point in what you say is that I keep left and right separate. I'm not going to contract what is, I would say, a left type color ordering with a right type color ordering. I want to keep them separate. Great. Okay, so the outcome is that the KLT kernel is the inverse of submatrices of my adjoint scalar amplitudes of those ranks. And that was actually noticed already from a different formulation of amplitudes, which is the scattering equation formulation or the CHY formulation that was noticed already then. Just let's see how it works at 4 point. So at 4 point, because I have to color order in 2 different ways in the bi-adjoint model, then the diagrams that I'm allowed to include are only the ones with channels that are compatible with both color ordering. So if I have the same color ordering 1, 2, 3, 4 on the right and the left, then I have both the S channel and the U channel. And if I combine those common denominator inverted, then I simply get S times U divided by T. And now there's a G squared too. This is exactly the kernel that I showed you before that canceled the S and U poles that were double in the product and provided the missing T pole. On the other hand, if I switch the color ordering in the second entry, so I have 1, 2, 3, 4, 1, 2, 4, 3, then the only common channel is the 1, 2 channel. So I only have the S channel, and it comes with a minus because of the antisymmetry in the structure constants of the cubic interaction. The inverse of that is, of course, just S, and there's the scale of the coupling, and that is exactly the kernel, the very first kernel I showed you in this whole story. All right, so what does string do compared to this? So we know now that the amplitude that should be the identity element amplitude from the identity element theory for string amplitude should be the inverse of the kernel. I gave you a kernel before, which was the sine function. If I expand that out, I see that the leading term is a -1 over S with some coupling. Now that is exactly the same as this theory here. So this is nothing but bi-adjoint scalar theory at the leading order. And then those amplitudes will have higher derivative corrections in odd powers of S. This was noticed already by Mizera, that all the endpoint 3 amplitudes of a certain theory of this form could encode the double copy kernel for string theory. So what does this all lead to? It leads to that there's an identity element also for the strings kernel. And in terms of the low energy expansion, it is the biadjoint scalar model plus some 2 derivative interactions, plus some 6 derivative interactions, and so on. And you see that it skips every second order because there are only odd powers in S. So for example, we can see that a 5 to the 4 operator was apparently not allowed from the point of view of string theory in terms of high derivative corrections to BAS. So what we can set out to do is try to understand these relations more generally and find the most general set of high derivative operators that are allowed from the double copy. And so that is really the program. We want to use this to bootstrap the identity and kernel, which are linked together. So that gives me the kernel and it gives me the identity. And then I can apply it to generalize the KLT relations and then double copy that. Okay, other questions? Good. Okay, I'll show you how this works at 4 point. So now that we have this identity that the kernel is the inverse of a submatrix of the identity element amplitudes, then it might appear that when I plug that back into this equation, which is the bootstrap equation, everything is trivial. But the fact is that it's not, because there was this choice of which n-3 factorial submatrices that I picked. And I may have to pick, I have the freedom to pick some so that they're not the inverses of each other. So let's illustrate this. So at 4 point, I have 6 independent color orderings, n-1 factorial, and I'll just list them in some particular order here. So let's pick out what this equation here, the bootstrap equation, actually says for rank 1. So I'll pick what was the gamma and delta color orderings to be 1, 2, 3, 4 both. So these are the black one and the red ones, and they're inherited on the other side as the color orderings that I inherit under the double copy. Then I pick the alpha and the beta in the double copy to be the color ordering 1, 2, 4, 3. So a different color ordering, which renders this equation non-trivial. So here they have the 2 different color orderings that I summed over, and I'm already using that the kernel is the inverse of the M4 matrix of these biadjoint type scalar amplitudes matrices. Okay, so that's my bootstrap equation. Let's multiply and rearrange it. And then we see that this is exactly the statement that a 2x2 minor of the entire 6x6 matrix of all possible color orderings has to vanish. That's exactly what the bootstrap equation said. But I just picked 2 random color orderings, 1, 2, 3, 4 for both, and 1, 2, 4, 3. I could have picked any 4 sets of color orderings in this 6x6 matrix. So this will necessarily tell me that the bootstrap equation is the statement that all 2x2 minors of the 6x6 matrix of color or doubly color order amplitudes has to vanish. But if all the 2x2 minors vanish, that's the same as saying that this 6x6 matrix must have rank 1. So what this is, and this happens at general at endpoint, is that the bootstrap equation becomes a rank equation on the matrix of all doubly color ordered identity element matrices. How do we solve this system? Well, there are 6x6 matrix of all color orderings, but they're not independent of each other because we have momentum relabelings and cyclic symmetry to relate each other. And in fact, you can parameterize all 36 elements in terms of just 3 functions that I here label. This is the F1, F2, and F6. Then, if you look at that 6x6 matrix with just parameterized by 3 functions, that has rank 6, if you know nothing about those functions. So if you impose the vanishing of all 2x2 minors of that system, it turns out to lead to 3 very simple equations. The first says that the function F1 is fixed by F2. F6, on the other hand, must be the same as F1. What does that say? That says that F6 has the trace reversal that if I read this trace backwards, it's 1, 2, 3, 4, 1, 2, 3, 4. So it says that trace reversal must hold at 4 point in order to get rank 2. Get rank 1. And then finally, the third equation is just sort of a self-consistency relation for the function F2 that parameterizes the color ordering where I flip 3 and 4 at the last one. So what solves these 3 equations? Well, it's solved by the field theory. It's solved by the string KLT kernel, or the identity element associated with that. It's solved by the amplitudes of the BAS theory also. And now the question is just what else solves this? So to understand what else solves this, I can parameterize one function, there's the F3, which determines everything else. And remind you that is the scattering amplitude for the 1, 2, 3, 4, 1, 2, 4, 3 ordering. So I write it as its leading BAS term. Here I've just included some lambda, which you can set to 1 in your head if you like. It's just a scale. And then I add to that all high derivative operators, which means all polynomials in S and T. Okay, now I plug in and I solve my bootstrap equations, the self-consistency condition here, order by order. That will place some constraints on these parameters here that I have here, the AKRs, which are just coefficients of the high derivative terms. These will be the Wilson coefficients of the high derivative operators. I must ensure locality, so I have to make sure that my amplitude F1 doesn't have any spurious poles. That places a few extra constraints on the parameters too. And systematically, what I then get is an expansion of my F2 function in terms of high derivative corrections to the BAS theory. If I compare it to what the strings kernel had given me from Misero's result, I would see that strings has A10 to be 0 and A11 to be -6 in some units where I match my G and lambda to alpha prime and pi. And similarly for the next order, the quadratic order in Mandelstam's A20 is 0 in string theory. At the cubic order, A33 is -7/360, and all the other coefficients must vanish and so on. So we see that clearly what is solved by this rank condition or this bootstrap equation is more general, strictly more general than what we have in string theory.
A small question. So you make a sort of power series ansatz. Could you also have some more general things like multiplying with logs or something like that?
Not at tree level. At tree level, everything has to be rational.
Oh, that's right. Okay, sorry.
The only other thing you could play with is the cubic interaction, and I'll say a couple of words about that actually just about now.
All right. Okay, thanks.
So if I translate that power expansion that I just showed you to Lagrangian terms at the lowest order, this is what it is. So the first line here is just BAS, and then I have two derivative corrections. And I've written them here in terms of three different type of contractions of the indices. And so what we have now, in addition to just the antisymmetric structure constants, are also the fully symmetric structure constants that enter, or sort of anomaly type of structure constants. Now there are only two parameters for these three terms, and I parameterize them as a left and a right, depending on whether my symmetric tensor structures sit on the right or the left in the story. And so these are just related to the A10 and A11 parameters. It's just a different way of writing those. So what do we see? First of all, we notice that we could have imagined another type of cubic interaction just along the way of Maria's question that had the fully symmetric structure constants instead of the antisymmetric ones. We could have included that, but that does not solve the rank 1 bootstrap equations. We also noticed that there's no phi to the 4 term, just like the string kernel didn't have that. And that's also because it just simply is set, its coefficient is simply set to 0 by the rank 1 bootstrap equations. And then we note that because of these symmetric structures, what is known as the U1 decoupling identity is going to be modified by these two derivative terms. And this is all well known because the string monotony relations also modify what is known as the U1 decoupling identity. Now, if we compare back to what string theory would have given us, string theory would have said a left equal to a right in this particular relation. And so in some sense, having a left and a right free here is a way of treating the left and right sectors differently, which is to say that we're treating left and right movers of the closed string differently. So in some sense, loosely speaking, you could think of this as some kind of heterotic generalization of the double couple. Okay, let's say a few words about what we can then possibly do with this. So here I now going to solve the generalized KK-BCJ relations, which come from the algebraic relations here, for Yang-Mills theory plus higher derivative terms. And so I systematically write my usual Yang-Mills theory plus all possible higher derivative terms at 4 point. So there's a pole term that come because I could have an exchange with two F-cubed vertices. That is known, that is there also in the standard double copy. But now we see that we're allowed to have an F to the 4. And this is good because such a thing is indeed in string theory, and its coefficient in string theory would have been fixed by alpha prime. But here we see that it's free. It doesn't have to have anything to do with alpha prime or anything else, but it is linked to the kernel. So anything that you double copy with the same kernel, this will be a fixed coefficient, not free. With the d squared f to the 4 operator, one is allowed, another one is not allowed, and this one is. So the other operator that could have been there could be proportional to s, but that is not allowed, as we see. And then you can go to as high order as we want, because it's pretty straightforward to solve. Now, if we then, and you can, of course, this was the left sector. You can do a similar thing for the right sector, and there will, of course, be an A right that sits there. Then we can double copy these two things together with a generalized double copy kernel. And here's what we get. So there's a lot of stuff here, but let me unpack it. So we get the 1 over s times t times u is the usual Einstein gravity term. Then there's an S channel, which arises from dilaton axion scalar exchanges, because they're going to be, when I have f cubed present, there's going to be an operator of the form scalar r squared in the effective action. That is known, and that is sitting here. Now, all of this in the second line or third line here, all of this is just one big coefficient that multiplies the local r to the 4 contribution. The terms with the green here is the standard thing that comes in the uncorrected double copy also. The new shift of that coefficient is parameterized by this parameter a to 0, which does not exist in string theory. Okay, and in general, this is what we tend to see, is that we generate from the double copy similar operators, but now with shifted Wilson coefficients and more, which allows more general structures. Let me give you just a schematic overview, just like I had before. I showed you in field theory KLT what was allowed by the field theory KLT KK-BCJ relations, but now what is allowed by the generalizations. We see that more operators are allowed, but there's still some selection principle present. Similarly for KPT, still things not allowed, but more things are allowed as input. Now, I showed you how this worked for the bootstrap at 4 point, but suppose we suppose we go to 5 point, then because we have a model for how to modify the kernel, the 5 point kernel, which is the 5 point higher derivative terms that are allowed for the corrections to the biadjoint scalar model, they will depend on the 4 point endpoint through factorization channels such as these ones. So we have to check that going to 5 and higher point doesn't certainly fix these free coefficients that we were so proud to have, because it's a win-win situation. Either it would fix us down to look more like string theory, which would be interesting, or we truly do have a generalization. So we've examined this at 5 and 6 point. And so just to outline at 5 point, there are 24 different color orderings. We can fix everything in terms of just 8 functions, solve the bootstrap equation, and systematically order by order, we find that there are no constraints placed on the 4 point coefficient. So these AIJs that were free before remain free and unfixed. And we have done this consistently up to 3rd order and Mandelstams. And in fact, even most of the first local terms that we see are totally fixed in terms of the 4 point input, no free parameters, until we get to higher point. Sorry, not higher point, higher order. And similarly, we have done this at 6 point, also tested all the rank 6 conditions, and we find no constraints on 4 point at the lowest orders that we have checked. So just to summarize where we have gotten so far, is that we have used this algebraic structure as a way to systematically find out how to generalize the kernel, leading to a certain rank condition on these 3 amplitudes of these identity element theories. Okay, so let me now turn to a couple of future possible directions. So why did I keep this rank n-3 factorial in the bootstrap equations? So the statement was that the leading order BAS model has this rank. So if I attempt to take a higher rank once I add higher derivative operators, which is the generic thing that happens, then I would have been in a problematic situation that when I go to low energies and these higher derivative operators become irrelevant, my inverse of these matrices which would now higher rank would become divergent, because as I take the low energy limit, I go back to BAS, which only has n-3 factorial rank. So it makes sense to only stick to this rank and not start to increase the rank if you want some sensible IR physics to come out of this without any IR UV mixing. But we could, of course, ask, what about bootstrapping for different types of ranks? What happens? Just if we take an open mind, we drop the idea that this should be bi-adjoint scalar plus higher derivatives, but say, let's start it somewhere else. Let's start it not with BIS, but the one with the symmetric couplings instead. What happens? And we have attempted such things, but in all cases, what we have found is that once you go to high enough order in terms of higher point, then the kernel tends to have spurious poles in it. And that means that you require additional cancellations to happen when you do the double copy. And it's not clear that that would in general happen. So it appears that the minimal rank, we at least have an indication that minimal rank seems to be a sensible condition for avoiding spurious poles in the kernel. Now, there's also another proposal for how to include high derivative terms in the double copy by Carrasco and his collaborators. And their idea is to use the BCJ form and then correct the color order factors. We can translate a few of their examples to ours, and in those cases, we always tend to find that that system is always the same minimal rank as we had there. So they formulate it in a very different way, but it seems to lead to the same type of rank conditions. One thing that's curious about what they have is that whereas we had this infinite tower of high derivative terms and thought about it in that way, they seem to have truncations of these infinite towers of corrections. Now, what does that mean for us? It means that our system should have truncations too. And indeed, if I took the left sector and removed this AL left, and I truncate my terms and just have that A right as the only correction to my BAS theory, then I do have an exact solution to the bootstrap equations. So here is one example of what the kernel would look like there. Here are examples of if I stick to the orders of the expansion there, I would just have the Yang-Mills theory on the left side. I would have Yang-Mills plus an f to the 4 on the right. And if I double copy those, the corrections in the Yang-Mills sector exactly cancel the corrections in the kernel. And I get some very bizarre relation that says that Yang-Mills times Yang-Mills plus f to the 4 is just GR without any higher derivative corrections. So this gives some indication that not all changes in the kernel and corresponding changes to what operators are allowed in the double copy lead to new results in the double copy relation, that there may be some freedom to move information around between corrections to the kernel and shift on the Wilson coefficients of the input and output. In particular, we have seen at 4 and 5 point in the examples we have checked that you tend in a double copy to generate the same type of operators, but with shift and Wilson coefficients. And so we have a proposal with a student of mine to find a systematic way of changing kernels. So basically having an algebraic structure that allows you to change from the standard BIS kernel without any high derivative corrections, but to that and the most general one using something that we call hybrid models. So maybe I will just in the sake of time, I will skip the details of this, but saying that there are some promising algebraic structures in the story, and you can ask me about it for those who are interested afterwards. The bottom line is that it appears that you can shift the Wilson coefficients in these systems and achieve the same result for the double copy. But that then raises another question, which is that we're starting to see from these S-matrix bootstrap ideas coming from a completely different point of view, that there are certain bounds on coefficients in high derivative theories. For example, there are bounds on what the coefficient of R to the 4 can possibly be. But if I have a double copy that shifts the coefficients, that will place bounds on what the parameters in the double copy can be. And that in turn will then feed back and be a way to potentially narrow down, to try to help us understand what makes the string kernel so special. It clearly has a special structure. If we can understand and narrow down to the string kernel, that will bootstrap us back in to having the open string amplitudes as the ones that solve the monodromy relations. And so it's a different way or a different take on trying to narrow us into what makes string theory special from a bottom-up approach. I just want to mention also that since these are tree amplitudes, they capture the classical physics. And so given that we have double copy at tree level, there's also been, of course, the proposal that the double copy would also work as a map from Yang-Mills solutions to the equations of motion to the solutions of Einstein's equations. And many people have been working on this from various angles for a variety of classes of solutions and in various different contexts. And so in that context, it's also relevant to ask how these generalized couple copies would fit into that classical equations of motion framework. And I'm also very curious to understand these underlying algebraic structures that we have elucidated here. How do they fit into the equation of motion framework? So with that, I'll finish with just highlighting the algebraic structure that we're using to bootstrap the double copy. And also thank my collaborators, my students who graduated in the past 2 years, and fourth-year student in Henriette, postdoc Hong Chi, and my new student, Alan Chen. And with that, I want to thank you all.
Okay, thank you very much. Let's thank Henriette for the very nice talk. Okay, so are there any questions? Then let me go first. Or Denjo, do you have a question?
No, my question is trivial, of course, but you have to go to infinite order to check that your generalization works. And how do you hope to do that?
So good. So we were, of course, in the event that we have gotten to 5-point and we have seen, if we had seen any sort of constraints on the 4-point parameters, we would have been concerned exactly about like point. I mean, do we keep getting new constraints even as we find new parameters at 5-point? Maybe 6-point would fix it. So it's a very it's a very positive for the point of view that anyway. So how should I say? I cannot go to infinite order, but it's already extremely strong constraints that come out of 5 and 6-point. In fact, at 5-point, the first order that you have corrections at 5-point, you have some freedom of fixing the constant terms in the 5-point effective action. And so you can always say, oh, I mean, I will always have some freedom to do that. So that's good. So, you know, maybe that gives freedom. But at 6-point, the leading order terms where the 4-point corrections start coming in are 1 over S. So that means that there are no local terms. I have absolutely no freedom to fix anything at 6-point in order to see any constraints, in order to resolve any constraints on A left and A right. And they pass these bootstrap constraints at 6-point without any constraints on A left and A right. This was in fact why we really wanted to do 6-point, because there was no freedom at 6-point for local terms or local parameters. No free parameters. It had to work on its own. And the fact that it does is to me a good indication that it's not all of a sudden going to go to 13-point and then provide constraints. But strictly speaking, we couldn't know. The other aspect of it would have been if we had started to see that these 4-point parameters were constrained at higher point, it would have been natural for it to happen much earlier and narrow yourself down to the string solution very early. But no, we can't go to infinite order, and we can't hope to do that. That's absolutely fair.
But perhaps you could hope to find a slight variation of the string version which incorporated your new parameters.
So that's what we have. I mean, the new parameters.
No, but from a derivation point of view.
Yeah. So I think another thing we have. I mean, we have exact equations that we're then solving perturbatively, basically. A different way of asking the question is: are there other exact solutions to those equations? Then I don't have to worry about going to higher order in the expansion, but I do have to worry about what happens if I have an exact solution at 4-point. I would have to have some solution at 5-point that has the correct factorization into that lower point solution. And that's deeply, deeply non-trivial. In fact, there is one other exact solution that we found, which is there's a theory called Z theory. And C theory, C theory amplitude solves the equation, but we don't know what to do with that as a double copy kernel in terms of the inputs of that. So there are, I mean, I think the first step here is to understand this algebraic structure better and show that there are general solutions. And I think there are different perspectives of how those parameters may narrow down to string parameters. But that requires additional input, not just the algebraic one.
But I mean, but you're working at tree level, so you don't need a fully quantized string.
That's right.
So you could imagine taking a variation of the string version, which is not consistent quantum mechanically, and obtaining
Right.
it from that point of view.
Yeah, I mean, but if I think about what yes, I mean, if I took the strings kernel or took this form that it has in the amplitude in the inverted form that Ms. Sarah gave, it basically looks like BAS theory with the propagators replaced by sines and tangents. And it's very hard to imagine how to modify that without messing up everything. It's sort of similar to when we first started out and we looked at the kernel. And then a very naive example, if I just add a new term that corresponds to basically adding some 5 to the 4, I immediately see things go bad. I can forget about my whole bootstrap and I can just see what does it give me. So it gives me at 4 point a rank 3 system instead of rank 1. And the kernel will have spurious poles. And then I can ask, well, maybe I just have to add some higher derivative terms that cancel those spurious poles, because now I'm summing over more terms. And you can actually play around with that. But the key thing here, I think, is always when you then go to higher point, you get restrictions from factorization, which are extremely non-trivial.
I appreciate that. I was thinking more that in the derivation of the KLT kernel, it began with, I think it was the open string.
Yes.
But now I could say, let me not pick a different open string theory, which is not a consistent theory from a quantum level. I know it's not going to work quantum mechanically, but it might give you a kernel which works at tree level.
Yeah, I mean, I think one
because
way
you have all these higher derivative operators, and you're not necessarily working with a normalizable theory. So
right, but so yes, but if I were to take something that looks like a string amplitude, I wouldn't know what to tweak in it. So the way I would think about tweaking it, and maybe this is not what you have in mind, but I would expand it small alpha prime, and then I would start tweaking it by changing the alpha prime parameters there. But then I'm doing exactly what I'm doing here, basically. Just from a top-down point of view, I'm saying what if the f to the 4 parameter didn't have just that -6, 1/6 in the coefficient, but some other number? What kernel would I have to let that pass? And that's basically the type of thing that we're doing here.
Thank you.
But it's definitely an interesting point of view. I mean, I think once we have the structure, then I think what you're asking is, like, rather than sort of brute force solving it, what else can we do with it?
Yes, essentially. It looks hopeless to try and go to order up to infinity.
Yeah, no, it's clear that we can't go much higher, right? I mean, it's clear that there are certain limits. Even 6 point is very complicated to expand in.
Okay, thank you very much. Appreciate it.
Great.
Any other questions? Yeah, I have sort of maybe a related question. Of course, this is all tree level, and it's not easy to go to loops, of course, but could it be that if you would do loop level, and well, could that affect your solutions here at classical level as well?
Yeah, so there's always this question of whether there exists a loop level version of KLT. And I'm a bit skeptical about that. I mean, I know that there have been some approaches, but there's some underlying reason that makes it seem not so plausible. So if you want to do loop level, the BCJ formulation looks like the better approach. So what JJ Carrasco and friends have done has been not as systematically to say what is the most general way I can do this, but more in the spirit of how do I include higher derivative operators, and if I want a particular one, what is the thing I have to do? And so my impression is that one thing that they have not done so much is look at the factorization constraint from higher to lower points, and also what is actually then the result of doing the double cover. So then if you have this BCJ form, then you can conjecture something similar to happen at loop level. And one context I think that he is very motivated by is the question of if I need to calculate in n = 4 supergravity to high loop order, at some point I will need to include local counter terms in the story. And so I would need in the double copy language to find a way of including those. And if I can produce them with the double copy, that's going to be an easier approach to do it. So I'm a bit skeptical about KLT for loop level. I don't think that's so feasible. Okay.
Yeah, thanks. So, and can you think of any other, say, imposing some sort of extra constraint that would sort of single out the string theory solution?
Yeah, so I think one thing we're doing here is completely bottom up, right? So we go from low energy,
yes,
and we're just saying what solves these equation and what can you get with it. So this is similar to the standard spirit of effective field theory, where we include all operators compatible with the symmetries with generic coefficients that we sort of expect at some scale to be order 1. And the only thing is that now we have some extra constraints on those Wilson coefficients because we require them to be compatible with the double copy. So the generalized KK-BCJ relations are imposed on those. So that gives some structure, but it's clearly not enough structure to narrow you down to say only this open string effort to solve this. So there's a paper not too long ago by Yutin Huan and collaborators who had the following idea. So they have this S-matrix bootstrap EFT hedron story. And basically, that is the idea that the constraints that there exist, sensible UV theory, meaning local, Lorentz invariant unitary, that will place constraints in the coefficients in the low energy expansion, such as positivity bounds and other bounds relating constants of different order. So if you took those EFT hedron constraints, and what he did was he then intersected those constraints with the constraints of the string monodromy relations, then he found very, numerically, but very close to precisely the open string. So he narrowed it down to that. But then you might complain, well, if you impose the string monodromy relations, you're sort of cheating a little bit, right? You're sort of putting some string stuff into it already. So what we can do now, and what I'm doing with Aiden and a new student, Justin Berman, is to ask the question, what if we don't impose string monodromy relations, but our generalized KK-BCJ relations? Do you still just get the open string, or are you left with any freedom? And if you get the open string and double copy it with a generalized kernel, what are the freedoms you have there? And how much? So anyway, the short answer to your question is you need additional information in order to narrow strings down. And the obvious thing to put in is UV completability. So that's where we're going.
Okay, thanks. Any further questions? Okay, if not, then let's thank Henriette again for the very nice presentation.
Thank you.
Okay, thanks again, and